Another property of waves, another characteristic of waves is frequency. It is very much like we use the word in common day language. How frequent something is how often it happens. In this case, how often the wave vibrates every second. That's what the frequency is. How often it vibrates every second, the unit that we use is hertz. 1 vibration per second is 1 hertz. The frequency is used as an identifier of the waves. It tells us what kind of wave it is. For example, for visible light, the frequency tells us the color of the light. For sound that we hear, for audible sound, the frequency tells us the pitch of the sound. We'll see examples of that. We'll see and hear examples of that shortly. Now, another characteristic of waves is what we call the wavelength. It is the length of the repetitive portion of the wave. The pattern that's repetitive in the wave. For example, as it is represented here by this double blue arrow, the wavelength is the distance between the crest and the following crest. So this is a wavelength. Or we could have started here and up to here. That would be a wavelength. Or we could have started at a trough and finished as a trough. A full pattern, a full repetitive portion of a wave is what we call a wavelength. The same thing applies for a longitudinal wave. From a compression to a compression to the next compression is a wavelength. Or from an expansion to the next expansion, that would be also a wavelength. Like for frequency, wavelength is used as an identifier of the waves. If you know the wavelength, you are going to be able to know what kind of wave you have. For visible light, like for frequency, the wavelength tells us the color of the light. For audible sound, the sound we hear, it tells us of the pitch of the sound. Amplitude, though, when represented graphically, like in this graph here with the double arrow, it is how high or how low the wave gets relative to equilibrium. Remember, equilibrium is the green line. So how high it is would be the height of the crest. So that's an amplitude. Or how deep it is the depth of the crest as represented here. That would be the amplitude. Think of it like the height of an ocean wave. Essentially, it tells us how big is the wave. The amplitude for light, it affects the brightness. For visible light, for the light that we see, higher amplitude means that the light for that same color is going to be brighter. Now, for sound, it's going to tell us for that same frequency sound, for that same pitch sound, a higher amplitude tells us that it is louder. Let's look at some examples of these. Here is the visible light. Now here we are going from high frequency to low frequency, or from low wavelength to high wavelength. This picture here, I just extracted it from the Encyclopedia Britannica website. Now, the frequencies here are given in terahertz, which is basically a huge number. When we read 750 is going to be 750 10 to the 12 hertz or cycles per second. That's 10 to the 12. It's bigger than the deficit. It's a huge number. And the wavelength, in this case for the light, is given in nanometers, 1/10 to the minus 9 meters. It's a very small number as well. Remember, a millimeter, which is a tenth of a centimeter, and a centimeter is about half an inch. So this would be a millionth of a tenth of an inch. So it's very tiny. That's what a nanometer is. We are talking of 400 nanometers to 780 nanometers. So, in other words, when we say, I have light at 400 nanometers wavelength, that tells me it's violet. If I tell you it's 570, that tells you that's the color. If I tell you 650, that's this color. So by giving you the wavelength, I have an identifier of what type of light it is. If I'm buying a light bulb, I can buy it based on these numbers. Alternatively, I can use the frequency. I can say, I would like a 675 terahertz light. That would be indigo. Or if I say 525 terahertz, that would be yellow, and so on. So it is an identifier of the light. We are not demonstrating the brightness of light here, but we are not demonstrating the effect of the amplitude here, but frequency and wavelength, they act as identifiers of the wave. Now for sound, we are going to try to demonstrate all of these properties. So in this case, since it is going to be sound, and you can get to these in YouTube, but I'm going to play them here. I'm going to play a 396 hertz sound. So that sound tells us we are hearing a 396 pitch sound. Now, to figure out the amplitude, okay, so what I'm going to do, I'm going to decrease the amplitude as you are hearing it. And increase it now. Decrease it. Okay. Hopefully that was not really traumatic to your hearing. So that's 396 hertz. Let's see how it is distinct from 852 hertz, which is a higher frequency sound. Okay, so you see how it is a higher pitch. I'm going to increase the amplitude, decrease the amplitude, increase the amplitude, decrease the amplitude. Okay, see, it's a higher pitch, but the amplitude is going to change for me how loud it is. Okay, let's finish this with a 5000 hertz sound. Okay, so this is a high-pitched sound, 5000 hertz. I'm going to decrease the amplitude. There, I decrease the amplitude, increase it. That's increased amplitude. That's decreased amplitude. I hope that this helps. So the frequency, I didn't write the wavelengths here, but the wavelength would have done the same thing. The frequency or the wavelength tell us of the pitch of the sound. The amplitude tells us of how loud it is.